Good morning. So today we are covering the optional material on Petri nets. And remember, we have the second midterm at, I guess, will be released around 6:30. And the rules are exactly the same as for the other midterm. All right, so we only have 1 hour or 50 minutes actually for Petri nets. So let's start right away. So patrons are a formalism that is not usually studied in formal languages, although, as we see, they define a formal language. They're used to model systems, software, processes. And the reason this is related to formal languages because, for example, if you want to use a patron to model a protocol, a communication protocol, for example, um, the specification for the protocol describe what are the sequence of events or actions that can happen in a correct communication. Like I request to send a message, then the system tells me you can send a message, then I send a message, then the message is received, etc., etc. Well, if each of these events is a symbol of an alphabet, essentially a pattern specifies the language of the legal sequences of events according to the protocol. So it's exactly a formal language, as we're gonna see. By the way, the name Petri nets comes from Carl Adam Petri, who is the person who defined them in his PhD, German guy. In 1960-61, he defined them, PhD thesis. He didn't call them Petri nets because he's, I guess, he's modest, but everybody else calls them Petri nets now. All right. So a Petri net contains a set P of places, and to make things simple, we just say they are P1, P2, dot, dot, P, let's say N, if I have N places. And T transitions, T1, T2, Tm. Okay, so there are some number of places and some number of transitions, and they are disjoint. Okay, so P intersection T is the empty set. Right? So they're nodes of a graph, and in fact, it's called a bipartite graph. And that means that a graph is bipartite if there are two types of nodes, in this case, places and transitions, and the arcs can only go from a place to transitions or from transitions to places, okay? Which means, so that we call them arcs, right? And the arcs are a subset of P cross T union T cross P. And from P to T, we call these the input arcs. And from T to P, we call these the output arcs. So input and output refers to the transitions. Okay, it's focused on the transition. Now, the most important difference from a Petri net to a finite automaton, for example, is that the state of the automaton is one of the nodes of the graph. The state of a Petri net is the number of tokens in each place. And we're going to draw it now. It's much easier to draw things. And you're going to see that Petri nets inherently are really useful to talk about distributed behavior as opposed to a finite automaton where you are in a state and then you move to another state. So transitions are drawn as bars or rectangles. Places are drawn as circles. So let's draw the pattern that we have in the nodes. Okay, so this is a Petri. The initial marking, so the marking is this. Okay? The marking is the number of tokens in each place. So initially, sorry, I think I messed. Okay, we need one here, right? Okay, place transition. And then we can write, for example, this is P1, P2, P3, P4, P5, T1, T2, T3, T4, T5. And we just named them so we can talk about them, right? So this is a Petri. Its initial marking is empty. Okay. If I want to do this instead, the initial marking is what? Well, is 1 in P1, 0, 0, 0, 0 in the others. And it is a vector of size n, the number of states, right? So this tells you that the initial marking, we can call it mu0, has 1 token in place 1 and 0 tokens elsewhere. We can also write it as P1 to the 1. And this is because the number of tokens can be greater than 1. So I could have a marking that is P2, 7, P3, 5. And that means I have 7 tokens here, 5 tokens here, and 0 tokens elsewhere. Right? So if these are the places, this will be the same as saying 0, 7, 5, 0, 0. Okay? It's so this is called bag notation because the marking is a bag. And the bag is the extension of a set where multiplicity of elements is counted, right? So in a set AB, if I add A to AB, I still have AB because it's a set. But if I have the bag AB and I add A, I get 2 A's and 1 B. All right. So the one thing you really need to keep in mind is this is not a state, this is not a state, this is not a state. These are places. The state is the snapshot of the Petri. So right now, the state is 1, 0, 0, 0, 0. Okay? So how does the Petri evolve? How does the Petri move? Well, we take any enabled transition T and we fire it. Okay? So a transition T is enabled if each input place has a token. So for example, here, let me change color. T1 is enabled, right? Because P1 is a token and it's the only input place to T1. Okay? So now we can fire T1. And when we fire T1, what happens is we remove all the tokens from one token from each input place, and we add a token to each output place. So now there is now the state is 0, 1, 1, 0, 0. And now you see the big difference between finite automata and Petri, right? Now I have 2 transitions enabled here. So this formalism, Petri, is very good to model concurrency because now I have the ability of firing T2 because T2 has a token in its input, or the ability of firing T3. So I can fire T3, for example, and I remove from P3 and I put it into P5. Now the only thing I can do is fire P2. And now what can I do is I can fire T5 because the input to T5 is P4 and P5, and they both have a token. Or I can fire T4 because the input to T4 is P4 and it has a token. So this is concurrency, but it's actually conflict. It's a special type of concurrency if you want. Because if I decide to fire T4, right, I remove this and I put one here. Now T5 is disabled, it's not enabled, right? So it was in T4 and T5 were in conflict. If I fire T4, I disable T5. And vice versa. Let's say now I fire T2 again. So I put it here. If I fire T5, I remove the token here and here, and I put it back where it was at the beginning. And now T4 is disabled. Okay, all right. So we have concurrency, we have conflict, right? So as you can imagine, this is really useful to represent human, mechanical, software activities, protocols, because in those activities, there are many things going on concurrently at the same time. Sometimes there are conflicts, and so on. So now, how do we get a language out of this? The way to talk about languages is to associate from each transition some labeling that to each transition associates a symbol either to sigma or epsilon, right? So for example, I can say A, B, C, B again, B epsilon, right? Okay. So now, as I play the token game, I let the tokens go around, I fire any enabled transition one at a time, but in any order if there are multiple enabled. I generate a string, right? Well, the string actually can go on forever, maybe, right? In this case, it would, right? Because this net can keep firing forever. So how do we define what are the strings in the language? Well, there are multiple ways, right? So first of all, there are three ways in which I can do this labeling, right? We can say, well, let me write it there. We can have a free labeling. Interesting enough, the free labeling is the most restricted. And each transition has a different label from sigma. Right? So I cannot have epsilon and I cannot have B and B. Then I have non-epsilon labeling, which obviously is no epsilon, but I can have B and B. And then unrestricted, which says any transition can be labeled with anything, epsilon or a symbol of the alphabet, including this. So this is unrestricted labeling, okay? Now, so I have three cases for the type of restriction I have on the labeling, and then I have two ways to define what is the language that I generate, right? Again, a language is finite strings, right? It's a set of finite strings. So I cannot just let this run forever, otherwise I would have, well, let's call it omega word, but it's not a string because it's infinite, right? So I need to define the finite strings are finite by definition of the language. So we have called L type, okay? And so a language, so given a Petri net M, places, transition, arcs, and the initial state. Okay. The language type L, given the sigma, the machine, and a set of final markings. So F are the final markings, is equal to what? Is equal to, so this labeling, we call it sigma, so let's put sigma there as well. Okay. This maps sigma into the transitions. So it's the sigma of a sequence of transition firings. So S is a sequence of transition firing, but that's not a string in the language. The sequence in the language is obtained by mapping this sequence of T's into a sequence of our symbols of the alphabet, or sigma. And from M0, the sequence S of firings goes to M, and M is a final state. Okay, so this is more similar to our notion of a finite automaton, right, where we say a string that leads from an initial state to a final state is a string in the language. So here, a string that leads from the initial marking to one of the final markings, well, it's not a string in the language, but when you apply the sigma, which is just a mapping from transitions to symbols of the alphabet, that's a string in the language. Otherwise, you can have a T-type, where T stands for trap, okay? Unfortunately, this T is not the T on the transitions. I cannot do fonts when I write on the board, but I can do them, and I did in the notes, right? So a T-type simply says given sigma mu and the mapping little sigma is the mapping of the strings that are sequences of transitions, and from mu 0, the sequence leads to mu, and mu is a trap, and a trap is simply a marking that has no enabled transitions. So it's a dead state, right? So unlike a DFA, where you can always set one more symbol, if a marking, for example, in this marking, if you could reach it, you can't in BizNet, but if you could reach the 0000 marking, it would be a trap. But by the way, it doesn't have to be 000, right? This also is a trap, right? 0001 or 5, right? Because tokens here are not enough to enable anything. You need tokens both in P5 and in P4 to enable P5, for example. So the interesting thing is that there are really 6 definitions of Petri languages, right? Depending on what you allow for the labeling and how you define what a string is, what the language is. So I think the best way to learn a little bit about Petri is to do a lot of examples now. So let's do that. All right, so let's talk about the language AB star. So is the language of epsilon, AB, 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 and so on. So that's definitely a regular language. And I want to generate with a free type. So each transition must be labeled with a different symbol of the alphabet. And L type. Well, sorry, a free labeling and L type. Meaning I specify a set of final markings, okay? So it's quite easy. Essentially is the DFA in this case, or close to the DFA. So I don't need to put an arrow there because what I draw is the initial marking. So the initial marking is 1, 0. And I need to specify the final set of states. And the final set of states is just the initial state of marking, right? So F is just the marking containing P1. 1 token in P1, 0 tokens in P2. How does this work? Exactly as a DFA in this case, right? So 1, 0 initial marking happens to be, or wait, let's write it this way, fine. Let's write it. There are really 2 ways to write marking, so let's just pick one. So P1 is the initial marking, is the final marking. So just for a DFA, if the initial marking is a final marking, then epsilon is in the language. So epsilon, right? But then what can I do? I can go, if I fire T1, T2, right? If I fire T1, I go from P1 to P2. This is not a final marking. But then from P2, I can go to P1 back, right? But to go from P1 to P2, sorry, I should have said, firing T1 generates an A, firing T2 generates a B. So when I do this, I generate an A. When I do this, I generate a B. Now I'm in P1 again. So I've generated AB. And I can do this again. I go to P2, generate an A. So now I generate AB. So actually, so this is A, but it's not in the language because it's not a final state. I generate ABA, but it's not in the language. But if I generate another B, I am back in P1. And I've generated AB, AB, which is in the language. Okay? So this is exactly your DFA. All I've done is add the 2 transitions there. So just labeling the edges here, I'm labeling the transition. So this is not really using patterns the way it's supposed to be used. Okay? But it's important to show that I can do that. In fact, there is a theorem that says that any regular language can be generated by L-type non-epsilon. Okay, this was also non-epsilon. Okay. If I wanted to do a T-type instead of an L-type, all I have to do is this. I still have generating here an A, generating a B. Right? So this was the L-type. But I need to go to T-type, which means I need to go to a trap state. All I can do is simply this. Now, I can generate some number of A's and B's. And again, those will be just strings I generate, but they're not in the language because the definition is only what I've generated upon reaching the trap state is in the language. But I can do any number here, and then if I do the epsilon, now I'm in a trap state because the net is empty and nothing can be fired. And so what that means is I can generate epsilon, so nothing, or I can do AB epsilon, or AB, 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 AB epsilon. Okay, so this is the same language generated by a trap type Petri net. But these are kind of regular type. Let's do something more interesting. So let's generate a context-free language. Okay, and this is L is the W in AB star such that the number of A's is equal to the number of B's. Right? We know this is not regular, it's context-free. And then let's do it with a T type, unrestricted. Okay, unrestricted is the easiest type, right? Because there is no restrictions. All right, so what is the idea? Here, you need to think, whenever it makes sense, concurrently, right? And this makes a lot of sense because this W has the number of A's and B's in any order. And so you can think of concurrently generating the A's and the B's. So this is a very typical way you will have to think about how to generate a language when you have some counting to do. Right here you have the number of A's, number of B's is the same. So start with P1. You can go here. P1. P2, P3. Let's call this P4. Let's look at this part for now. So here again, you can fire T1, which just does an epsilon. But when you fire T1, there's this typical pattern behavior, right? This is P1 is a control place for T1 because as long as P1 is there, it controls the enabling, right? So when T1 fires, it needs to have a token in P1, but then it puts it back. Okay, so firing T1 does not remove the token from P1, or if you want, it removes it but puts it back. But every time T1 fires, it adds a token here and here. So if I fire T1 3 times, I will have 1, 2, 3, 1, 2, 3. The important thing is that I have the same number of tokens in P2 and P3. But at some point, I decide, well, I don't want to keep doing this. I want to fire the other epsilon. So now I move the control token from P1 to P4. Okay. Now what do I have? I have the control token in P4, and I have 3 and 3 there. Well, it's perfect because what can I do? I simply can have this. So now A and B are both enabled, or T2 and T3, right? They're both enabled. And every time they will fire, they will leave the token in P4, but they will decrease the number of tokens in P2 or in P3. But the nice thing of pairs is that they're concurrent, so this can happen in any order. So I can do T2, then T3, then T3, then T3, then T2, then T2, for example. Okay. Well, that will be then what will be A, B, 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 A, which is in the language. Okay. What happens when both P3 and P2 are empty? I still have a token in P4, but that's not good enough because to fire anything, I need to have something in P2 or something in P4, in P3. So that means that I'm in a trap state. And that means that what I've generated so far, which is an equal number of A's and B's, is in the language. Okay, so this is typical pattern type thinking. An important thing is that very often you have conceptually or informally maybe control places and data places, right? So you can think of P2 and P3 as data is the end that you would have to decrease, and P1 and P4 are the control logic. Essentially, if you're talking in P1, you're generating increase in the end. When you go to P4, you stop in, you decided the n is what it is, and it is both here and there. So that's one thing that push down automata cannot do, right? Here you can have many copies of n if you want. And then you can use the n you non-deterministically decided to now generate the same number of A's and B's. Okay, so this is a very typical way of thinking about Petri nets. Any questions on this one? Because that's the first one that is really different thinking from finite automata. All right. What about the language of balanced parentheses? Right? So we have looked at this, right? So is L equal the W in open, close, star, such that the number of open is equal to the number of closed, but that's not enough to balance, right? For all x, there exists a y such that xy equal w implies, so for all prefixes of x, and y is the suffix, corresponding suffix, the number of open parentheses is at least as large as the number of closed. In other words, you don't close a parenthesis before you have opened it, right? And so the number of x which are open is less or equal the number of x which are closed. Okay. All right. And so now we do again, we do an L type. So let's draw the pattern first. It's actually very nice and simple. This is simpler than MPDA. This is simpler than a context-free grammar. So this is the open, and this is the closed. And simply this final state is final if it just has a token in P1 and P2 is empty, because P2 is empty means that you have generated as many closed parentheses as you have generated the open ones. So how does it work? Well, the only thing that can happen at the beginning, I can open a parenthesis, and every time I fire, let's call them T1 and T2, every time I fire T1, the token remains here. So this token never goes away. But if I fire T1 3 times, I have 3 tokens here. So the string so far is what? Is open, 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 but it's not in the language because it's not the final state. However, I can fire P2, sorry, T2, and T2 removes, right? So, for example, I can do this, and I go here. Then I can fire T1 again, and I add another open, but I also add a token. So maybe if I fire 3 times P2 now, this P2 becomes empty. So I have a string in the language because the marking is 1 in P1, 0 in P2, which is the D final state. And the string is in the language. Why? Because I generate as many open as closed. And for sure, the only way I can generate a closed is if I generated the open before. Okay? So this is a very elegant way to do this language. And it uses concurrency in a sense because while I can always generate T1, sometimes when I have tokens here, I can also generate T2. So open and close concurrently, right? As long as I have tokens here, the next thing that can happen is either firing T1 or firing T2. Okay? So this is again is another example of a context-free language. Which I can generate with some type. So when I say I can generate with Petri, I need to be a little careful because again, there are 6 ways to define the language for Petri, right? Based on the labeling I allow and whether it's L or T type. Okay, let's do another one. A to the n, b to the 2n. Again, n natural number, of course. Well, this again is a context-free language. Let's use a T type again. So I start here. I generate just an epsilon. When I want to stop, or so this is similar to what we did before. So this is an A. So this is T type. How does it work? Initially, similar to before, yes, to the other one, I fire A n times, and after that, I will have n here and n there, and I've generated A to the n. And as long as the token is in P1, I cannot generate any B. Because to generate B, I need to have the token here. So this again is the control token. But so I generate some n here and here. And then what? Well, the only thing I can do at some point is say, well, I'm tired of generating A's. So I go to P4. Once I'm here, the only enabled transitions are these 2. And I can fire either one as long as I still have n's here. And since this is a T type, I can only stop when both P3 and P4 are empty. And then I will have generated NBs from here and NBs from there, so it's going to be B to the 2n. Okay. Now, if you have looked at any Petri book or paper or whatever, you can actually simplify this because the definition of edge of arcs I gave you is very, very simple. The more normal definition is I can say 2 there, and meaning when I fire this transition, I generate an A, I take the token from here, I put it back, and I put 2 tokens there, not 1. It's called the cardinality of the arc. It's 2. Well, that means what? That means that if I generate A n A's, I will have 2 n tokens there. And then I can do that, right? Or I could have done it in another way. If I don't want to use arc cardinalities, I can do what? Well, I generate n b's, right? So this would generate a to the n, b to the n, right? But then I could do this. Right? And so this would, similar to the other one, right? I would generate these and these would both fire n times before I go to a trap. So there are a few ways to get the same. The simplest one is to allow a 2 there, and then I just count twice as many tokens right away. If you have any questions on how they behave, so now you probably are wondering, I kind of said, right, that all regular languages are Petri languages, at least if you don't consider the free labeling, which is a very, very strong restriction. It's exactly not free very much, right? You have seen now a few context-free languages, which I can do with PetriNet. So if you have an inquisitive mind, the next question you would have is, well, what is the relationship between context-free languages and PetriNet languages? And the answer is really interesting. So first of all, we're going to show that there are non-context-free languages I can generate with a PetriNet, and it's actually quite simple to see there that so a to the n b w such that the number of C's is equal to the number of D, and is equal to n in W, okay? So, in other words, a to the n, and then a B is a separator, and then W, but W is of length 2n's, which would be context-free to check, but the number of C's is equal n, and the number of D's is equal to n. That's not context-free, you can prove it, right? And obviously it's not context-free because you have to count 2n 3 times, not 2. And when you do the second match, right, or in other words, here you can easily do this part, but not make sure that this n is the same as that n. So that's definitely not context-free. You can use the pumpkin lemma to prove it.
No, but I think even though that it's
Is there a
closed,
question?
the thing is that it's not a day before.
So is there a question? Yeah, okay. So let's do the Petri for this, and we're gonna do a L type or T type. It doesn't matter. And let's do, I guess, unrestricted. We'll see. Okay. So P1, we start with a token. So this generates the A's. So this part does what? This decide n, right? So this generates n A's and puts n tokens there and there if it generates a to the n. Then at some point, it generates a b, and now I'm here. And now I have n tokens here, n tokens there, and one token here. And I want to generate the same number of C's and D's as I have n's there. But that's very easy. We just did it, right? So all you have to do is C and D. And you use the token in P2 as a control. Right? So if you play with this net, you will see that it does exactly what it needs to do. It generates exactly this language. It generates some NAs, then a B, and then it starts generating C's and D's in any order until these N's go to 0, at which point you've generated a string in the language, and the only token is in P2, everything else is empty. So you can call this a T type, because now this is absorbing, or you can call it an L type, where you say that F is equal to just P2. Because if you have token only in P2, you happen to be a trap. Okay, now, interesting enough, so this is a non-context-free language, but it is a Petri net language. Interesting enough, and this is because you have these free ends, right? There is also the reverse. For example, WWR, right, or whatever, W in AB star, right? We know that this is a context-free language. Well, the last theorem, which I have no time to go over, is essentially a pumping lemma type argument, shows that this is not a context-free language. So the conclusion, which I think is very interesting, is this. We have regular languages, and everybody knows how to do those, right? So we have context-free languages, which include the regular languages. Well, we have Petri languages, so there are all regular languages of both context-free and Petri languages. We have seen a few languages that are both context-free and Petri languages, but we saw a language which is Petri but not context-free, and I told you, the proof is in the notes, that there are context-free languages. One of them is this one, that is not Petri. Okay? So really, they are a different way to talk about the class of language, which is, somewhat comparable to context-free, right? We're going to see, as of next class that there is then this huge set. I guess it's the whole whiteboard. It's not everything, right? But it's the Turing acceptable, etc. languages, right? But the nice thing of these languages is that we can talk about them. For example, we know that, so this is very interesting. We know is W in L, this question, right, is W in a context-free language, is answerable. Well, guess what? This one is answerable here as well. However, patterns were defined in 1960-61 until 19, I think 80 something. Nobody knew whether this question was answerable, whether there was an algorithm to answer membership for pattern languages. And it finally was answered in the positive, but I think over 20 years later, right? And patterns are not used as much as context-free languages, so there are still, as I list on the notes, several interesting open questions. But the closure properties that we know for pattern languages are they are closed under concatenation, under intersection, under reversal, nobody knows whether they're closed under complementation, at least last time I checked. They are not closed under clean start. They are closed under concurrency. While instead, context-free languages are not closed under concurrency. What is concurrency? Concurrency is if I have two languages, I take a string from one, I take a string from the other, and then I stick them together in any order. So if I have A, B, A, whatever, right? And I have 0, 1, 1, 0, etc. Then I can do A, B, 0, A, 1, 1, A. So I interleave the two strings in any order I want. That's concurrency, right? Because essentially they are going all concurrently. Well, patronets obviously are closed because all I have to do is the two patronets, I just let them run together and they generate a string in any order. Context-free languages are not closed under concurrency. So they have different properties, which means they're useful for different things. When you want to talk about concurrent systems, patronets are usually a very good choice. Okay, end of the lecture. There is a optional homework on patronets. I encourage all of you to do it. One, because patronets are fun, and actually they are used. It's conceivable, unless you become a compiler writer or something like that, it's conceivable that in your job, you might actually end up using patronets. I wouldn't say more than context-free or push down, but depends on the type of job you have. And then the other good reason is because you can raise your grade. All right, good luck on your midterm, and I'll see you at office hours.